Thanks everyone for coming. I think you're probably aware, but just as background, Ming's presentation looking at climate change issues in the Kimberley is part of a large Kimberley Marine Research Program. We've got 25 research projects that are going on there, and Ming's obviously inputting into part of that process, and his data is also used in some of the other projects as well. So we've been working with some of the researchers. So I'll allow Ming to provide the information. We've all got a sheet that Joe has helped put together with the leaflet. These are available on the actual website, and in order to, and Kelly is also recording, I think, the process as well through a way you can hear the audio as well as the PowerPoint presentation. That'll be available online at the same time. So please go to the website to see more of that. And Ming is also working on his final report at the moment, so that will be available online as soon as that's produced as well, to sort of complete up the package of that sort of work. So without further ado, Ming, I'll let you.
Sure. Thanks. Yeah, thanks, Stuart. Thanks for all coming for this seminar, I guess. So this is for project 2.2.7. First of all, I'll acknowledge the team members from CSIRO, Dirk Slavinsky, Kenji Shimizu. He has left CSIRO now, I guess, work in private company. And Ning Zhang, who was a PhD student working with me in CSIRO from Ocean University of China. So this work also being contributed by Xuebing Zhang, Jessica, Susan, Yan Du, and Jim Greenwood as well. In fact, I mean, Jim, I, and Kenji kind of co-developed the regional downscaling kind of model for the Kimberley coast. So I will introduce, I mean, later in the talk. So here is an outline of this talk. So first of all, I think I better give some background on the climate drivers of ocean state of the Kimberley coast. So then I will move on to introduce some of the observed variability of the Kimberley. So focus on sea level, precipitation and salinity, ocean temperature, and possibly focus a little bit on the marine heat waves. We know that there was a big event in early 2016. So then I will move on to introduce the future climate downscaling and projections. So there are two models. One is the global ocean model. It's developed by CSIRO from people based in Hobart. And the other is the regional model that Jim and I and Kenji developed for the Kimberley coast. So then I will maybe discuss of the key kind of gaps, knowledge gaps from this project. So, okay, first of all, I mean, for climate drivers, I mean, so we know that the Kimberley coast is in the tropical north. So the tropical kind of ocean atmospheric kind of climate variability will definitely affect the coast environment in that region. So the biggest probably signal probably in the world ocean atmosphere system is called so-called kind of ENSO, El Nino and La Nina. So so sometimes people use Darwin sea level pressure as a proxy for ENSO. So you can see, I mean, it's important for the region. So the three panels shows the three conditions. The top one shows the normal condition. So normally we have a warm pool probably in the Western Pacific, which and in the Indonesian seas as well, which drive this kind of deep convection to form the cloud cover in that region. So we know that due to that kind of process, the region receives more precipitation, probably 2 to 3 meters per year on average in the Indonesia archipelago and kind of region, and probably Darwin, Kimberley kind of coast as well. So that's a normal condition. So we have the trade wind probably from the American coast blowing across the Pacific toward the Australian kind of landmass. So what happens in El Nino? So when El Nino occurs is when the warm water in the Western Pacific kind of moved to the east, to the Central and Eastern Pacific. So the region there is warm up, so carries all the kind of deep convections, the cloud forming with it. So left behind is probably in the Western Pacific is a cooler kind of temperature. So the heat content get kind of lower and less rainfall as well. So you can see there's if you saw the arrow, there's a downdraft. So which means it brings the dry air to the area. So we know there's a drought probably condition probably in the eastern half of the Australia during El Nino year, and that affects the Kimberley coast as well. So the opposite would occur during La Nina. La Nina is when the trade wind kind of strengthens, very strong. So drive a stronger kind of a convection, convergence and convection in the Western Pacific and off the Kimberley coast and Indonesian archipelago as well, and drive a stronger kind of convection and more rainfall. So we know that eastern half of the Australia receives much more kind of rainfall during La Nina years, especially probably one of the record kind of rainfall occurred in the general area was during the 2010-11 kind of La Nina. So we know that during that event, we also have the probably one of the strongest kind of warming event across the whole WA. I mean, killing all whole kind of coral bleaching in Ningaloo, Broadus, and down even Rottnest Island. So climate variability is important for the region. So this is one phenomenon called ENSO. And on the other side of the equation, we have the Indian Ocean. How to move forward? Okay, the phenomenon called the Indian Ocean dipole. So it's very similar to the Pacific. It's a kind of seesaw kind of pattern between East and West Indian Ocean, like the Pacific. So we have a cooler condition in the east and a warm condition in the west, which is on the left panel. So drive more rainfall to the west, and probably a dry condition, not in the Kimberley coast per se, but probably down south, extending to Victoria kind of state, I mean, kind of region, even Tasmania. So that's a dry condition for the region. We know that probably all the significant drought, I think a Federation drought, probably a drought of bushfire, probably a few years ago, are induced by this kind of event, Indian Ocean dipole event. So that's kind of a driver for this. Yeah, for the southeast kind of climate. The opposite occurred on the right panel here. So that's a negative Indian Ocean dipole. When the west of Indian Ocean get cooler and east Indian Ocean get warmer, so you have more rainfall probably in the tropical northwest extend to Victoria coast. So that's the Indian Ocean dipole. So Pacific and Indian. And so we know that we can use some indices to describe this kind of phenomena. Pointers. So I highlighted kind of three kind of years, I guess, which is three kind of major El Nino event. So one is in 82, 83, and the more recent one is 97, 98. People would know that, probably causing coral bleaching in the Great Barrier Reef and Scott Reef as well. And the more recent kind of strong event is in the 2015-16 kind of El Nino. So we know that Kimberley coast and Scott Reef also got probably coral bleaching, roly shows, and there's a massive kind of coral bleaching in the northern kind of GBR kind of region. So that's when the index is positive, we call it El Nino, and when it's negative, it's La Nina. So we can see that 2010-11 is a kind of reasonably kind of strong kind of La Nina. So it coupled with some local processes and caused the coral bleaching of and fish kills of the west coast of Australia in 2011. So Indian Ocean dipole often kind of co-occur with El Nino and La Nina, so which is the index is shown below. But there are some independent kind of events. For example, the 94 kind of event of El Nino. There's no kind of a co-occurring kind of El Nino in the Pacific. So okay, that's a kind of a basinal kind of mode. And also, I mean, this mode will affect the onset of the Australian monsoon as well, so or the strength as well. So this is how the Australian monsoon is defined. So we carve a box, probably from 5 degrees south and around 20 degrees south, and in the northern Australia, we use the eastward kind of wind speed as an index for the Australian monsoon. So on the top left panel, this shows you the seasonal cycle of this index. So when the wind blowing eastward, we call it onset of the Australian monsoon. And when you switch to westward, is when the trade wind kind of start to blow. I mean, so we know that the onset of Australian monsoon in the region means more rainfall and start of the precipitation kind of cycle. So we know that normally the monsoon starts in December and lasts until January, February, and probably stops sometimes in March. So that's a normal process. And on the lower panel, we showed the January and February when the monsoon for these 2 months. So also highlighted are the 3 years of El Nino. You can see that during these 3 years, there are very weak kind of Australian monsoons. So 82, 83, 97, 98, and the recent one, 2015, 16. Very weak kind of Australian monsoon. So which means less cloud, less rainfall, and probably somehow associated with marine heat waves we observed. I will kind of discuss that probably in later. So these are the 3 kind of things we have talked about, and there are a new phenomena called Madden-Julian oscillation. So this is a phenomena that is a convection process, a rainfall process that propagates from the Indian Ocean in phase 1, slowly move to the northern Australia region in phase 4 and 5, and then move to the Pacific in the later phase 6, 7, 8. So that's a deep convection process. So we know that when this occurred, it also has a wind kind of anomaly associated with that. So this mode doesn't look like the El Nino and Indian Ocean dipole, which is seesaw kind of mode. This one is a propagating mode, but it has a very kind of short time frame, 40-day, kind of 60-day kind of cycle. So we know locally, we have the weather pattern probably propagate from Western Australia, kind of south coast, to South Australia, then the east coast. So the weather pattern probably at a frequency of 7 to 10 days. So that's a high latitude. But in the tropical, it's a similar kind of phenomenon. There's an eastward propagation of the weather pattern, but at a lower frequency, at a 40 and 60-day kind of frequency. So this phenomenon is important for if we know the cycle of this kind of the variability, we can predict when the rainfall onset probably during the monsoon season. So for the Kimberley and probably the Northern Territory kind of region. So people use a diagram on the right panel here to show how this kind of evolve. So it's like a cycle. So basically, to rotate a circle probably within a month or less than 2. Okay, so these are the phenomena we have to deal with. So there's probably ENSO, dipole, MJO, and they all interact with the Australian monsoon. So how we observe the variability in the region? Probably I will start from sea level and then move on to the other phenomena. I will discuss how these variability are linked to this climate variability in the coast, in a large scale kind of pattern. So first of all, sea level. So we choose probably 3 stations: Darwin, Wyndham, and Broome. So it's labeled on the right. So this is just the seasonal cycle. So basically, the sea level is high during summer, probably late summer, February, March, and lower in winter season, June, July, August. So that's a normal. Probably we know that in summer it warms the ocean expands, cause high sea level. But also when the Australian monsoon onset during the December, January season, the eastward kind of wind also pushed probably a high sea level kind of head set up in the Gulf of Carpentaria kind of, and along the northern kind of Kimberley region. So this is kind of the probably seasonal cycle of sea level. But when we look at the interannual kind of long-term trend, what we found is probably during La Nina year, there's a high sea level. For example, the 2000, you can see probably in all 3 stations, the sea level is higher than normal around 2000. And probably in 2010, 11 as well, so probably higher kind of sea level anomaly, which is due to the La Nina phenomenon. So we know La Nina will drive more warm water in the region, set up a higher sea level head in the region. So that's probably La Nina will cause the coastal wave propagation, probably affect the whole kind of coastal current system. So we know that the sea level has a rising trend as well. So if you look at the Broome, it has probably more than 50-year kind of record. The trend is roughly, I can't remember the number, between 2 to 3 kind of millimeters per year during the 50-year kind of record. and probably there's an acceleration during the more or less the last kind of 20, 30 years. So at a trend of between 5 to 10 kind of millimeter per year. So we know that is due to both of the slow kind of climate kind of change kind of forcing and some variability as well. So it's the same probably trend for Wyndham and Darwin kind of sea level as well during the same period. So okay, so we now move on to precipitation. So this is the data acquired from CSIRO and the Bureau that we made a joint high resolution kind of precipitation product for Australia. So this is a precipitation rate, a monthly average in the Kimberley kind of region. So the top panel shows monthly. I think the lower panel break that time series into the monthly chronology. So it's average over the whole record. So we can see that the rainfall probably jump much higher in December, which means the onset of the Australian monsoon, and lasted in January, February, and probably March. In April, probably the Australian monsoon kind of died off when the transition into the trade wind kind of regime. So the rainfall, I mean, during this period, I mean, I think the lower panel is average over the wet season rainfall year by year, and we can see that during La Nina year, indeed, there's a heavy kind of precipitation. Probably one of the record rainfall occurred probably in 2010-11 kind of La Nina event. You can see it from here. So during El Nino years, the rainfall tend to be lower. So the time series doesn't extend until probably to last year. So we don't have the graph for the 2015 kind of El Nino event, which could mean much lower kind of rainfall than this. So more rainfall means a lower salinity. So that's what we have simulated and we have observed. So we used IMOS data kind of stream to observe in the region to look at salinity variability, and we also used various kind of Argo kind of product and other data sets. But this is from the model which assimilate all the data sets and use the realistic kind of rainfall to drive the model. What we can see that is during the 2010-11 kind of La Nina event, what we just saw that the record rainfall in the region. So the salinity in the region probably is reduced by between 0.3 to 0.4 kind of PSU during the peak. So it's I don't know how significant is that for biology. I think probably it's important, I guess. I mean, for some species, I guess, more sensitive to salinity than others. I think if you look at the evolution, the low salinity signals start to occur probably in the Indonesian seas in August, then slowly evolve southward in October and December, and peaked probably in February. So when the peak of the El Nino kind of occurred. So then it's kind of carried by the lower current, kind of wrapped around the Western Australia coast, kind of influence the local salinity of the West Coast as well. So even, I mean, at the Rothney station, we observed for more than 60 years as a national reference station. So we observed very low salinity at that station during that year. So that's the salinity response to the climate variability. So we know that I'll now move on to ocean temperature. So this is a very simple kind of a plot of the seasonal variations of ocean temperature. We know it's hot probably in summer and cooler probably start in July or August, and probably start warm again in the following kind of summer. So the black line is a 200-meter contour there, and they can see that, yeah, there's a nice kind of seasonal cycle in the region. I think we are doing some work to show that maybe there's a double peak in seasonal cycle. So that's kind of still a work in progress to better understand what's the driver of this seasonal cycle. So I think there's some suggestion that during the monsoon and trade wind transition period, there's more likely to have an enhanced kind of ocean temperature variability in that area. So look at the long-term trend. This is probably from the trend starts from we calculate from 1981 up to 2015. So this we don't see a strong trend in the region. as compared to the West Coast. I think we published some work with Alan Pierce probably quite a number of years ago. I mean, saying that of this coast, West Coast of Australia, is one of the hotspot of global warming, probably in the world ocean. But in Kimberley coast, we don't see that during the past kind of record, except probably in November, December, in probably just before summer, there's a kind of a warm kind of trend. So that's the observation, and but there are some variabilities. I mean, so I presented this at the WAMSI symposium at the AMSA last 2 months ago, I guess. So we published a paper in Scientific Report by Ning Zhang, my student, and so we looked at the variability of the ocean temperature with El Nino La Nina kind of cycle. So this is a composite. I showed you 3 El Nino events, right? But there are probably 7 or 8 El Nino events during the from 1980s up to now. So we put the data together. We come up with this composite, so the average condition during El Nino. So the top left is during the pre-El Nino kind of winter, and then the top right is a pre-El Nino kind of spring, and the lower panel is a summer and autumn kind of season. So we can see that during El Nino, probably prior to El Nino peak, I mean during the spring season, you do see the cooling signal. We know that during El Nino, I said before, I mean, the warm water kind of shifts to the East Pacific, and this region is generally cold. But from spring to summer, there's a quick transition from a cooler signal in the region to a much warmer signal. So you can see that probably the temperature anomaly is strong in summer. Probably, I think if you look at the monthly signal, it's peaked in March kind of season. That's when the region was observed coral bleaching, and also near the Great Barrier Reef. I mean, probably the last peak of their coral bleaching event also occurred in March, kind of 2016. So why El Nino would drive this kind of warming signal in the region? So this is a composite of the Australian monsoon index I mentioned earlier, but using daily kind of data. So the normal condition is a light blue line, and La Nina condition is a blue line, it's a heavy blue line. We can see that during La Nina, the monsoon strengthened. So I mean, this is consistent. We have more rainfall, a stronger wind. But during El Nino, which is a red line here, so the monsoon kind of wind kind of weakened. So I think the wind fluctuation would impact on the ocean temperature as well. So if you look at the evolution of the 2016 kind of El Nino or marine heatwave in the region, which caused kind of Scott Reef kind of coral bleaching and in other regions as well. This is a paper we are on the review. I mean, so these are monthly kind of anomalies from September 2015 up until probably November 2016. So probably more than a year kind of time series. I mean, so you can see that the warm signal is red means a warmer anomaly, and blue is cold, but in the region probably for the whole year it's warm. So probably most striking, I mean, so probably the peak of the warming occurs in March 2016, and I think the precursor of the warming start from the northwest shelf and extended probably eastward during the following months, and probably decayed probably in May and June the following year. So for the Great Barrier Reef, but the warming probably extended further during the later winter months of the Kimberley coast. So, but the winter warming doesn't cause coral bleaching, but still probably significant for biology. I mean, this kind of winter warming, we speculate is due to the Indian Ocean dipole. Is that there was a negative kind of Indian Ocean dipole during 2016. That's Jessica's paper. I think, yeah. So now come back to the question: why El Nino would drive marine heatwave in the region? So we know that El Nino has 2 factors. One is it brings all the cloud from the Kimberley coast to the east. So the whole area has probably during the El Nino peak has a very clear kind of sky. So clear sky means you would allow more solar panel radiation enter the ocean, so to heat the ocean up. So there's another factor, probably is a cooling factor, is due to the wind. So normally, I mean, the two can be balanced. You have solar radiation into the ocean, then you have wind to cause evaporation, to cool the ocean. So these two terms balance. But during El Nino year, there's a stronger solar radiation into the ocean. But as I said earlier, monsoon wind has weakened. So the monsoon wind, weakened monsoon means there's less evaporation, kind of cooling. So both factors contribute to the strong kind of 2016 kind of warming. This is also from Jessica's paper. So I plotted probably from December to March, December 2015, January, February to March 2016. Of the left panel is a short wave radiation, the middle panel is a latent heat flux, and the right panel is 2 to 8 flux. So you can see that short wave radiation does contribute, I mean, significantly, probably in January and February, to warm up the ocean. This is an anomalous kind of flux, so it's much warmer than normal year by probably 50 watts per square meter. That's a big number. So, and also the latent heat flux is also a warming kind of signal, which means it's a reduced kind of latent heat flux in January and February. So we can see the net heat flux, the total heat flux, is into the ocean on the order of between 50 to 100 watts per square meter in January, probably lower in February. So this warming in these 2 months would cause the peak of warming in March 2016, causing the coral bleaching event during that month. So okay, so then we look at the I think we try to compare Kimberley coast with West Coast. So we wrote a paper. That's a paper by Ning as well. So how likely, I mean, the marine heat wave would occur during different kind of climate extremes. So I think this is the frequency of marine heat wave, and this is duration, how many days per summer month there's a marine heat wave, and this is total intensity. At 2 reefs, we have chosen 10 typical kind of reefs for the whole WA. So from Cocos Island, Christmas Island, Ashmore, Scott Reef, Kimberley, Rowley shows as a tropical reefs. So we found that in this kind of red circle kind of region, these reefs are more likely to have a coral bleaching or marine heat wave events during El Nino, when you have a clear sky. But in the southern kind of reefs, in the subtropical reefs from Montebello, Ningaloo, Shark Bay, and Borealis, so it's more likely to occur during La Nina. Why La Nina instead of El Nino? So we know that that's due to the Lunar current. Lunar current is a warm current. So during La Nina, lunar current strengthens, which brings the tropical warm water southward, carries all the way to probably from the tropical region along the coast all the way to Borealis and Rottnest. So the different processes. I mean, so in the tropical ocean, it's just clear sky and lower kind of Australian monsoon. In the subtropical ocean, so it's a boundary current. I mean, when it strengthens, it carries more warm water to cause kind of damage down the south coast. So it's a kind of probably bring a broader kind of perspective of the Kimberley kind of research we have been doing. So okay, probably on and on. So the MJO event also caused some intraseasonal variability of the marine heat waves. I'll probably will skip that. I mean, so what it means is, where does a marine heat wave peak occur? It's just before the onset of the Australian monsoon. So the ocean warms up, so it drives the convection process to bring the rainfall. Just before that, probably you would see a peak of the marine heat waves. So I probably will skip that. I mean, so I'll give you a summary of how the climate variability affect the ocean state of Kimberley. So sea level probably its annual cycle is due to the monsoon winds kind of transition, and the interannual variation is mostly due to the Pacific kind of ENSO, and that will drive the boundary current variability as well. I mean, like the Holloway current and Lowland current. And the precipitation probably mostly due to ENSO and with contributions from Australian monsoon, and we have a very high kind of rainfall during the 2011 kind of La Nina, and tend to have a lower rainfall, lower precipitation probably during El Nino events. So ocean temperature is due to mostly due to ENSO and to some extent due to Indian Ocean dipole. So we described that. Probably I think the last point just showed earlier. I mean, El Nino will cause more likelihood of coral bleaching in the tropical ocean, and La Nina will cause more likelihood of coral bleaching probably off the west coast. So now this is the third part. And people are still following me. Yeah, I hope. I mean, so yeah, you can interrupt if you have any questions. I mean, so I just kind of follow my pace. I mean, I hope you can follow as well. And so it's a climate downscaling prediction. So we use two models. So first of all, I introduced the global model. So it has been used by CSIRO for almost 20 years. We call it a blue link model, or officially it's an OFAM, Ocean Forecast Australian model. It's a 10-kilometer kind of resolution model from probably 75 to 75 kind of north, 75 south. We don't have the polar kind of regions. And it's a global model. It's 10 kilometers. So we did 3 experiments for I think this is jointly funded by a CSIRO strategic kind of internal project. So we did 3 experiments. One is a historical run. We ran the model for 1979 to 2014. And then we did a future climate prediction under the RCP 8.5 forcing. We know that in IPCC report, probably there's a consensus that the RCP 8.5 is on the higher end of emission now. So probably people think, oh, we are starting to take measures to control the CO2 emission. Maybe the future trajectory will follow a lower kind of emission kind of scenario. So this would be the model produced by this experiment would be on the higher end of the future warming and prediction. Also, we did a control experiment so that we make sure that the model doesn't drift due to the internal model kind of physics. So the model is pretty good to capture the ocean current around Australia. We published one paper in GGR to describe the general kind of ocean current around Australia, how it's captured. I mean, for example, the Indonesian through flow, the lunar current on the west coast, and the turn into South Australian current, the Flint current, and then turn northward to form the lunar undercurrent. So, and also the Eastern Australian current is well captured by this model. Anyway, so all the map shows the surface velocity. So anyway, so this is we look at the Kimberley coast. So this is the January map of the surface current versus July. So as I mentioned, probably in January when you have the Australian monsoon, the wind is eastward. So it stopped stops the Holloway current flowing along the coast. So you can see that in January, probably due to the wind is kind of eastward, probably you have some very coastal kind of eastward current. But once the wind stopped, so you can see the onset of the Holloway current probably flow along the Kimberley coast all the way to Pilbara, and some of the water mass will join the lunar current off the west coast. So now it's briefly. So this is a linear trend of the model simulation from 2006 to 2100 in the OFAM simulation for the future kind of climate prediction. So the ocean will warm at a rate probably on 0.03 centigrade per year, or 0.3 kind of centigrade per decade, or 1.5 degree probably over 50 years. So that's kind of the model projection. So we know that is a high CO2 emission scenario. So if you have a lower kind of scenario, this trend might be more, let's say, modified. I think it's a warming trend that would be 1 degree per 50 years. It's kind of like reasonable for the region, I guess. I mean, so one signal you found is the coastal region is a warming kind of faster than the offshore. So this is, which is indicated by the yellow kind of symbol here. So one paper is more or less related to the Kimberley project we published is the alarmingly kind of reduction of the Indonesian through-flow transport. We know that the Indonesian through-flow transport drives the low current. So I think from our model simulation, and we checked with other kind of global model, IPCC kind of scenario as well. So we found there's a similar trend. So the Indonesian through-flow will reduce by more than 30% in the future climate. So under this kind of simulation, under this scenario, so which is due to the reduction of this global kind of deep water kind of formation. So the implication of this for the lunar current, we still need to kind of better understand. So I think a reduction of the through-flow transport warm water into our region. So when the through-flow weakens, which means the region subsurface will become cooler. So surface become warmer and the subsurface become cooler, which means there's an increase of stratification in the water column. I will show it later on. So, okay, so now I move on.
When you say surface, how deep are you talking?
Okay, I think, yeah, I think there's a map here on the lower panel here. So this is the warming we mentioned, probably in the top 100 meters. Okay. And the through-flow contribution is a cooling signal between 200 and probably a few hundred meters. Yeah, so I'll only go through this a bit briefly. I'm probably okay. So we working with Jim and Kenji, we come up with a 2-kilometer resolution kind of Kimberley model, because we found that the model available is not suitable for this kind of downscaling work. So we developed this model based on ROMs, and the model has 30 kind of vertical layers, and we set a minimum depth at 7 meters. So some of the coastal process, very shallow water kind of process, won't be captured by the model. So this model is nested within the OFAM model I mentioned earlier. So for that model, we did a 100-year future projection, but for this model, it's too expensive to do that. So we took some slices. So we did a 4-year model around 2009 to 12, and a 4-year for 2016-9 to 66 to 69, 4 years for the future climate. So we just compared the two kind of slices. I mean, I think that's probably what we showed here. I guess, okay, January and July. So the future minus current, so the warming trend. So one signal we can see here is that the cooler month for the Kimberley coast probably will be warming faster than the summer months. So probably July, you can see the coastal region warm faster. So we haven't explored what would drive this yet. I mean, so one possible reason is probably during winter, in the normal conditions, the water column is stratified. Sorry, it's not stratified. There's a deep, there's convective process. Probably the water is well mixed. But with the slow warming in the future, even in winter, the water column in the region will be stratified. So which probably is demonstrated as a faster warming for the July winter kind of season. So this is a vertical profile for one section from the Kimberley coast here and all the way to probably Scott Reef around here, and all the way extended to the deep ocean. So the middle panel is just the average temperature, January to March. I mean, so in the 2000s. So it's the current climate, and the lower panel is the future minus current. So we can see that there's probably around 2 degree kind of warming in the top. Probably you hard to see the numbers. Probably up to 2 degree, I would say. I mean, so and there's subsurface warming, probably subsurface kind of slightly kind of cooling. Is likely due to the reduction of the Indonesian through-flow in the model in the future climate. Okay, so I'll probably move on a little bit on the. I think you probably heard Nicole Jones and others work on the internal waves in the region. I think the internal waves or internal tides is a mechanism to bring the deep nutrient probably from the shelf break here onto the shelf. I think Jim's talk probably touched on that as well. So we know that. So this shelf break here is a key region for internal wave generation. So this is an internal wave generation kind of index. So high means probably more likelihood to generate from here. So when the wave is generated, it's propagated offshore and onshore. The onshore propagation will carry some nutrient onto the shelf. So briefly, I mean, one result from the study, we haven't published anything on this yet. I mean, we don't know if we'll have time to publish, but we will try. I mean, so this is the internal wave energy for the current climate. So you can see that the shelf break probably is here. So most of the energy kind of propagate offshore, but there are some kind of onshore propagation. So which shows in the kind of pinkish or purple kind of color. So what amazing is, I mean, due to the stratification kind of change, we see enhancement of the internal wave energy on the shelf. So by probably more than 50%, or even in some locations 100% increase of this energy, which means probably in the future, due to the stratification change, internal wave maybe generation doesn't change, but the propagation will enhance. The onshore propagation will be enhanced, which means, I mean, for internal wave propagation, you have to have a stratification. If the water is uniform, there's no propagation at all. So which means, I mean, something, I guess, in the future, probably the region is nutrient, probably on the shelf will be more likely kind of supplied by increased amount from the offshore. So so the implication needs probably a further study. So okay, so probably here's a summary. I think I will skip that. I think most of the point I mentioned already. So fast warming near the coast, Indonesian through flow weakening, and the stratification will change the water column kind of structure and the internal wave kind of dynamics. So what are the key knowledge gaps? I sent the report to Kelly and Stuart for them to review, and they come back, oh, you haven't kind of addressed these questions yet, or you haven't kind of addressed those questions properly. So I have a ponder through that. I mean, so if we want to do a new study, what kind of project we want really develop? I mean, what's the gaps we found? I mean, so I think one thing is, I mean, the marine heat waves. I mean, so whether we can improve our capability to predict marine heat waves in the region. So, for example, we can give the managers probably 2 weeks or 1 month kind of lead time to know that there will be a peak event occurring in the region. So you can take measures to mitigate the potential impact. So that's a potential project that we can deliver. So in fact, I have just developed a project with CSIRO and with a group of scientists in China to do some offshore experiment in the region. So we will do some field work in the region to measure the airship heat flux. As I mentioned, probably the solar radiation is important. The latent heat flux evaporation is also important. We want to do some measurement during the next 2 summers in the region. So that's another kind of multi-million-dollar project jointly funded by CSIRO and our international partners. So we hope, I mean, WAMSI will continue to support, probably doing some more modeling using our regional model to see whether this kind of climate variability or MJO cycle El Nino would impact on the coastal water column stratification, coastal current, and probably regional impact on the coral reefs. So that's probably one area we want to kind of to explore. The other, probably Stuart mentioned a few times, I mean, we know that stratification will change in the future climate. So, but how stratification affect the onshore transport of deep nutrient and the vertical mixing of nutrient, the recycling process on the shelf, we don't know. I mean, we don't have a baseline knowledge yet. So basically, we need probably more measurement on that, and also probably we need to have some modeling exercise to evaluate against these measurements during different kind of ENSO phases. So we can use that to better quantify the future climate projection and how that impact on coral reef and other ecosystems in the region. So maybe another area was ocean connectivity. I think in the other project, probably Catherine and Ollie, I guess.
Ollie.
Ollie Berry, sorry, yes, my colleague, but he moved to the other other programs. So yeah, that's the beauty. I mean, so they have done some work. I'm using our model, 2 kilometer reservoir model to look at the seagrass connectivity and even fish and coral. I think they only used our model under the current climate. So we haven't explored, I mean, I think we said we would explore that, I mean, but we didn't, how the future climate change would impact on the connectivity for the region. So that would be another gap. So probably we potentially can explore. Okay, so that's all my talk. Thank you.
Any questions on me? That's probably 3 talks in one there. So any questions on any of those talks that Ming presented?
Okay.
We're going to be having a bit of a discussion with Ming after this, with I think Sean and a couple of people about some of the outputs of the project from a management implication perspective. So certainly we'll be taking some of this further to try and really tease out, as Ming was referring to the end, what does this mean for managers? And that's it's really important for science to understand what's going on, but critically in the short term, what does it mean for managers and their ability to both manage and plan, I suppose, the region. So we'll be looking from that perspective to try and understand better how this will influence what we're doing going forward. And the difficulty with climate change, as everyone knows, you can't really stop it. So how do we best understand what's going on in order to go forward? I mean, I was going to talk some more about how there's obviously Lu and current being really important. If the Indian Ocean through flow is being reduced,
yeah, okay.
There's a whole lot of implications, not just for the marine heat wave, but also ecologically, I suppose, down the coast as well.
Yeah,
so,
yeah. I think we haven't kind of so explore that. I mean, so what means by a weakening Lu current? I mean, you can see that the subsurface is kind of cooling. I mean, so we are changing the thermocline kind of structure.
Yes.
I think one probably for Ningaloo, I guess, if you have a shallow thermocline, which means upwelling will get stronger.
Yes.
What does that mean? I mean, yeah. So I think a weaker Lu current means probably the lobster will probably change their behavior, I guess. I mean, so.
Is it likely to reduce that? Because I know there's been a lot of talk about that sort of tropicalization of the southern oceans.
Yeah.
Will it reduce that tropicalization and almost reverse the?
No, I think So the surface layer warming is obviously there. So I think the figure I showed. I mean, the top 100 meters.
Yep.
So air sea flux kind of cause a warming will continue. I mean.
Yes.
So the cooling occurs in the subsurface.
Much deeper.
So all the kind of marine life probably live in the top 100 meters, I guess, more or less. I mean, so yeah, the tropicalization process will still occur, probably at the pace we projected.
Mm-hmm.
But the addition to that is the subsurface kind of ocean dynamics. So weaker through flow and weaker Lu current. What implication of that? I mean, maybe will affect the ecosystem in a different way. So.
Yes. Okay.
Yeah.
I have another one if no one else has one. Just in terms of, you've got the Indian Ocean dipole, obviously working in the Indian Ocean, and you've got with the seesaw pattern, and the La Nina, El Nino events occurring on the other side.
Sure.
Do they tend to? You could have extreme events if they coincide, or you could have they reduce each other if the seesaw pattern works in opposite directions.
That's right. Okay, that's a good question. I mean, so normally they could occur to a certain extent. The Indian Ocean dipole probably peaks in July, August, September, up to probably October, sometime November.
Yep.
But El Nino peaks later, December, January, February. So they peak in different seasons, but they do tend to occur. Sometimes, I think for Kimberley, marine heat waves, when they do occur, I think Indian Ocean dipole will cause a cooling signal in the Kimberley coast, and El Nino later on will add a warming signal. So when they do occur, I think the warming signal probably marine heat wave wasn't that strong. But in 2016, the Indian Ocean dipole event didn't occur.
Just didn't occur at all.
Yeah, it's a very weak event. So El Nino event probably impact is on the not a cooling state. Its impact on the relatively kind of warm state of the ocean. Yeah. So
is this a cumulative effect?
So I mean there are other occasions. Probably for rainfall, probably there's a it's a complementary kind of impact for these two phenomena.
Yeah. Okay.
Yeah.
Are there any other questions of me? Otherwise, if you can put your hands together, thank you very much for as I said before, this presentation and all of the products coming out of this particular project will be available on the WAMSI website, and Alita will be certainly circulating this newsletter that comes out, a visual newsletter on a regular basis. So if you're not on that, jump online on the WAMSI website and sign up there. Alita's our communications person at WAMSI. So if you join up there, you'll receive those things and more information comes out. So thank you very much for coming. Appreciate it.
Thank you.